Professor Amit Agarwal, Professor, Department of Mechanical Engineering, IITB Mumbai, to deliver inaugural address and to continue with technical talk. Please.
Good morning, everybody. It's my pleasure to be here. I would first like to thank Dr. Bimla Juliet for this kind invitation, and I would like to welcome all the faculty members and all the participants of SRM, all the faculty members of SRM and all the participants of this course for coming to this program here. So of course, this is, if you look at today's world, there is a lot of talk about development of micro devices for various bio and other interesting applications. And this is what this course will introduce you to. I'm sure there are a lot of very interesting talks covering various aspects, whether it is materials, whether it is fabrication, whether it is thermal. So I'm sure you will be exposed to a lot of different ideas, and that is, so I'm sure you will go back enriched after this course. So I think that's all I have to say as far as the opening remark goes. And whenever you want, I can start off with my lecture after this. So I don't know, you want me to start the lecture immediately there?
Yes, sir. Yes, sir. You can start the lecture, sir. Yes, sir.
Okay, fine. I will do that. So I will start sharing my slide. Yeah, okay. I will start sharing my slides.
Yes, sir. Yes, sir, please. Yes.
So good morning, everybody. I'm sorry for this delay, due to this technical delay, I should say. So here we are going to talk about, because as we know that this is a course where we are looking at a point of care lab on a chip devices. So I'm going to talk about some of these devices that essentially our lab has made in the last few years. Two of those devices are shown here, and the emphasis will be to see and understand how one goes about making these devices. So the broader objective of this work, or the presentation that I'm going to make, is to develop kits for human health monitoring and disease diagnostics. So this is an example of what we mean. Of course, we know about pregnancy kit and glucose meters and such things which are there in the market, which are essentially doing one or the other of these tests. So of course, that has made our life convenient in the sense that the result of pregnancy or blood test or blood sugar is so much more easily being obtained as compared to whatever was happening maybe a decade back. So the objective is to be able to make more such devices which can monitor the human health functioning, and it can help figure out if there is any disease which is there. So of course, if you're looking at it from the engineering point of view, the requirements that can be posed are this device should be easy to use, it should be cheap, quick, and it should require a small amount of sample and so on. But we know that meeting all these requirements is not very easy, and this is that's why the whole subject essentially is become so interesting and relevant for us in today's time. So let me start off with one example. This example is from a literature, but where the idea is that we try to make measurement of dopamine from whole blood. So you see that this is the device which is there, and this device, essentially there are two main devices or main components which are there, or one which we call that as a sample preparation module, and the other one which is a sensor module. The sample preparation module is where the blood comes in and something happens to this blood, and whatever is interesting or relevant for you, which is plasma in this case, which is what you see here, comes out. And by the way, this is the separator that we have actually created. This is our design, and we'll show you how we went about designing this. And we are essentially using this as an example because this study has actually used our device to do this test of dopamine from blood. And the second module, which you see here, is a sensor module where this dopamine is then taken and sensed, or the amount of that is sensed. So again, just to emphasize, just to sort of summarize, we are saying that any device is expected to have a few modules. Here we are looking at two main modules. One is the sample preparation module, where the blood is taken in, which is what you see in the left, and the plasma comes out. This plasma is now going to have and indicate the amount of dopamine which is there. And to do that, we take this plasma to a second sensor module where we essentially sense the amount of dopamine which is there, and therefore we know how much dopamine is there in blood. So these are the type of devices that we, if we were to sort of measure, if we were to look inside this box here, this is the type of device that is what we will be seeing. So our objective of what I'm going to talk about here are, we are going to talk about, we have made a few devices. The first one is the blood plasma separation micro device. We have already seen a picture of that in the previous slide, and I'm going to elaborate more upon that. We also have a device where we can enrich platelets from blood. We can also use for three-dimensional hydrodynamic focusing. Maybe this is a new term for some of you, so I will explain that later on. And then maybe we'll have a constant wall temperature micro device. So our objective here is to be able to see how what design principle these are based, and how does we go about doing designing these, and so what is the basic principle of operation or around which we can make these devices, and how can we separate out and focus and do other things. So let me start off with the first module, which is the blood plasma separation device. And one can ask the question, why do we need to separate plasma from blood? So the answer to that lies in the fact that once a patient goes to a doctor, the blood test is one of the first tests which is recommended by the doctor. And this is because plasma has plenty of biomarkers and analytes, which gives us a very good indication of the human health functioning. And therefore, the efficient detection of these analytes requires that there should not be any interference from the other interfering things, which could be cells. And therefore, we would like to separate out the cells or remove the plasma, and then just work with the plasma without the presence of the cells. So therefore, the separation of plasma becomes an indispensable process for disease diagnostics. And to remind you of what is there in blood, the blood has several solid components, and then it has liquid components. The solid component are what you see here are the red blood cells, which, as this table shows, are around 8 microns in size, and approximately 5 million of these RBCs are there per microliter of blood. So one drop of blood is a few microliters, and when you draw out blood, you draw some milliliters of blood. So you can see that we are now going to deal with several millions to billions of these cells. And these are all 8 microns in size. Then we have white blood cells, which are relatively large, much fewer in number. We also have platelets, which are much smaller in size, and relative to WBCs, they are more in number. So if you were to picture a blood, huge out, then you will see that at the bottom, the red blood cells will be deposited, and then there will be a region where it's so-called the Buffy region, a Buffy coat, where the WBCs and the platelets will be sitting, and on top of that, the plasma is sitting. So as we have seen, the plasma is what is required for further testing of the sample, and conventional way of separating plasma is to just centrifuge things. So you take blood collected from the patient, you centrifuge it. It separates it out into various components, like what we have discussed. But of course, this whole process is very energy consuming. It also involves multiple stages of handling of blood. And of course, if you are doing so many of these patients together, then there is a chance of mislabeling and I mean, the errors that can be lead to error in what the type. So, I mean, basically, you may just think of that this is what patient A is showing, whereas it is actually being shown by patient B and so on. So the idea is that can we replace this centrifuge and do the same thing of plasma separation on a microfluidic platform, which has several advantages. For example, it reduces the amount of blood that you would need. And therefore, if you're doing a chemistry or chemical based testing, then the amount of the reagent that you would need is also going to be reduced. And therefore, the cost which is involved, because mostly the reagents are very costly. So the amount of cost per test can be reduced that way. Of course, you can see that they are going to be very portable. So this is the device that we ultimately landed up making. Of course, I'm going to discuss further about it, but this is an overview of how the device would look like. So you can see that this is a coin-shaped device in every sense, or it is even smaller than a 2 rupees coin. So you can actually carry it in your pocket. And this is something that can be then tested, or this device can be used at the site of the patient itself. So the patient need not go to the hospital. Whatever is being done in the pathology lab can be done with this device at home, sitting at home. So let me just, so the problem statement that we are essentially looking at now is that we would like to separate out plasma from blood. And because the plasma has all these analytes and other biomarkers of interest, which can be then sensed, like what we have shown earlier. It can be sensed from these various viewpoints. So the question arises, if we just want to separate out plasma from blood, can we not use a filter-based device? So you just use a filter which will block out the cells, which is the solid part, and let the liquid part or the plasma flow through, and that can be collected, just like you make tea, and you use the strainer to remove the tea leaves. Can we not do that? The answer to that turns out to be no, or it's difficult to use a filter because we have seen the numbers. The numbers showed that we're dealing with 5 millions of RBCs per microliter of blood that we take. So as we said, a drop of blood would be at least 10 or even 20 microliters. So then that means that we're dealing with something like 50 to 100 millions of these cells. So that means that these cells will come very close to the filter and they will block the filter, and therefore the filter will no longer allow the plasma to pass through, and the filter will get clogged. On the other hand, what you would also find is that because these RBCs, although they're 8 microns in size, and although these filters or the pore size in the membrane may be like 1 or 2 micron in size, these RBCs will deform themselves and reduce their shape, their size, and they will actually be able to pass through these pores. So what you would find is initially you collect good amount of RBCs on this side. So it's not pure plasma that is getting collected on the other side. And after some time, everything stops coming altogether because you have a layer of these cells which have formed here and which has clogged this filter, and nothing is really coming out on the other side. So this is a major issue with this filtration-based device. You can also think of that whatever is of interest can actually get absorbed on this membrane surface or this filter surface, and therefore very little will come out on the other side. So that means that the sensitivity of the test has also reduced. So you can see that these filter-based tests have a lot of these disadvantages that we have talked about, and therefore we would like to move away from these filter-based devices. Although this is one of the first things that one would think about doing. So you can see that in later studies, these are studies from the literature, 2012, 2014, people were trying to uh, use some sort of a difference in their design. Here, what you can see is that instead of having a head-on filtration, you have a cross sort of a filtration, a lateral sort of a filtration. So you sort of bring here the blood, it passes through this passage, and you are hoping that some of the plasma in the process will ooze out and get collected here. But you can see that these elements are again very similar to a filter-based elements. It's a mechanical blockage that has been created, and that mechanical blockage is expected to reduce the flow of the cells, especially the RBCs, from here to your plasma collection line. But this is still a filter-based sort of a philosophy over which the separation is happening. And so therefore, all the disadvantages of filter-based things that we have talked about apply to this design as well. So of course, people have tried to again get rid of it in other ways, but these are all, or a lot of them are filter-based devices. So we have to now having realized that filter-based devices are not going to be good for us. This is of course another study from the literature where people realized and started to use some sort of a hydrodynamic forces, and this is what we are also going to use. So, and that's why we are talking about this device. So you can see that there is blood which is fed in from one side. It passes through these very intricate shapes which are given here, and the zoomed view of one of these shapes is shown further here. And then it gets collected from the two sides. The plasma gets collected from the two sides. And in between, you can see that the blood is made to pass through this 20 micron or this 40 micron size passages. And we have seen that RBC itself is 8 microns in size. So that means 3 of these cells coming together is good enough. At the same time, is good enough to create a blockage. So you can see that this is a very, first of all, you can see this is a complex design. You can see making it is going to be very difficult because of all these intricate features that you have. And then it involves small dimensions, and these small dimensions makes it prone to clogging. And therefore, these devices are not going to be necessarily very reliable in field operation. So there are several, of course, so these are some of the devices that we have seen. And of course, there are a lot of other devices that one can look at. But so we have looked at two major categories of devices, one which are filtration based and the other one which are these hydrodynamic based. And we realize that there are issues or limitations with these existing devices. And of course, those things are summarized in this slide. And the major being that these devices, so most of these devices are actually demonstrated on diluted blood. So what you do is you say that I will take 1 part of blood and maybe 5 parts of buffer. I will mix them and then I will flow it. If you do that, then you are artificially reducing the number of cells, and that reduces the number of the problem of clotting and other issues that we have seen. So our sort of objective was to be able to design a micro device without the need for dilution and something which is easy to make, and it works on a relatively simple design. So what I will describe next is how do we go about making such a device. So we have to understand it is going to be based on certain physical principles. So we have to understand what are the physical principles that are going to be involved here. We call this as a biophysical effect or a biophysical principle because this is seen primarily with blood, and therefore it's like a sort of more like a biophysical effect. So what happens, this is an observation which was made by Farias sometimes back, maybe almost like 70, 80 years back, that if you take blood and flow it in a small passage, you will see that the cells tend to move away from the walls. So you can see this is the dark line, which is essentially the wall. You can see the dark line on the top. These are the walls of the microchannel. And then you see that there is a thin whitish region. This is the region which is free of cells. And then you see this darker shade in between. This is where the cells have migrated. So you can see that there is a lateral migration of cells which is happening. The cells are avoiding to go very close to the wall. This is a natural phenomenon that happens. And if you have to understand why this happens, if you look at the shearing which is happening, so the shearing is maximum at the wall and minimum at the center. So the cells have a shear-induced migration, or they tend to avoid regions of high shear. So therefore, they tend to move away from the walls and tend to move towards the center. And this is a nice effect that one can exploit. For example, if I just, we are going to exploit this effect. And this is the so-called the Farias effect, which we can use to make our device once we understand that something like this happens. Now, we can also talk about an interesting effect, which is this bifurcation law, the Zhai-Fang-Fung bifurcation law, which is also a biophysical effect, where if you bring in the cells and to a bifurcation, the cells have a choice to either take this upper branch or move in the lower branch. And what has been observed is that the cells will tend to move in the branch which has a higher flow rate, provided some of these conditions are met. So this is the other interesting effect. So if you can create this, then you should be able to see, or you can utilize this effect, and you can make cells move in a certain passage, preferred direction, and the plasma move in the other passage. So using this, we could make our first generation for micro device, which is a very simple T-shaped sort of a thing. Blood comes in from the left, and all you have is a T-shape or a junction like what is shown here on the picture schematically, and this is an actual device where you can see this white region, which is again the cell-induced cell-free region, and then you can see from the difference in the color that you see a lot of this plasma. There is almost none of these red dots, which are indication of the RBCs, are actually flowing in this part, and everything is flowing towards the right. Of course, here the issue is that this is very diluted blood, and in diluted blood you can see this effect, and you can make a very simple device. But if you have to not dilute the blood, then you will have to you have to do more changes or further changes to your design so that you can work with whole blood without the need for diluting it. So this is another interesting effect, which we call it as a geometric effect, because here we play around with the geometry. So what we do, if we pinch the thing, this is very similar to what if you take a garden hose and you pinch it at the end, you just block it. Pinching essentially means just blocking it at one end. You see that the flow rate increases. And you can throw the water from the garden hose to a further away pot. So that's what happens here as well. So suddenly there is a pinching that's happening, and because of which these cells tends to migrate or tends to accelerate. And then suddenly when this pinch is released, the area cross-sectional area is increased. The velocity will suddenly drop. And by that time, I mean, essentially the cells will have their certain amount of momentum. The liquid part will have a certain amount of momentum, and there is difference in the momentum, which will help to separate out these two things. And that's what you would see, which is happening. So you can see that there is a very clear cell-free region which is formed. So this is a more whitish region as compared to this darker region. This darker region is where the cells are flowing, and this whitish region is where the plasma is coming out. And then you can connect a side branch, and you can skim out the plasma from here. You can also bring in another geometric effect like what is shown here, a centrifugal force, by bending the tube, and then you can make things flow like what is shown here. Again, from the difference in color, you can see very clearly that where the cells are and where the plasma is. So this is everything putting together, you can see that the blood is coming in from the bottom side here. The bottom side is where the blood is coming. It passes through this bend to bring in the centrifugal forces. You have this bifurcation to bring in the bifurcation effect. You have a small sizes to bring in the Farias effect. So you can see that all these things have been nicely put in here, optimally put here, and you are able to get plasma which is coming out from this side, and the remaining thing, the concentrated blood, essentially flows towards the left here. So, and of course, you can see from the quality of this picture that you have a very high quality of plasma which just comes out of this device. And it is a very relatively simple device to work with. And you can do a detailed quantification of the results. I will not get into too much of that. So this is just some flow cytometry based results. This is for whole blood. This is what you would get from a centrifuge. This is what you would get from our device. And what you see here, this is the lobe, which is an indication of RBCs and WBCs. So this lobe essentially vanishes in this case as well as in this case. So from our centrifuge, as well as if we put it in our device, this lobe essentially vanishes, which means that the cells have migrated as we were claiming. And of course, there is a lot more quantification that one can do. And of course, this is a comparison of the design with several other designs in the literature. And you can see that it performs much better than any of these designs which are there. And to summarize, so we would, I mean, this device essentially gives us almost 100% suppression efficiency with whole blood. There is no need to dilute the blood. And in fact, you can go the other way. And even if there are more number of cells than what is normally happen, which happens in certain diseases like polycythemia, we try to consider those cases as well, and we still could get very good suppression. At least 80% plus suppression was available with us. And this involves reasonably large flow rates. So you can see that typically when we, in a syringe, we would collect around 5 ml or 3 to 5 ml of blood. And you can see here, if you have to process that amount of blood, blood volume, then I would need only like something like 6 to 10 minutes to handle 3 to 5 ml of blood because of the flow rates that are involved, which is a very reasonable time to do the suppression of the first step. Of course, this point was not emphasized enough, but this is another interesting features where we are working with relatively large dimensions. All dimensions are essentially greater than 100 microns, which avoids the problem of clogging and other things that we were talking about. And what it also means is that even if I make 1 micron or 2 micron error in trying to, when making them, so 100 becomes 101 or 102 microns. So it still is like 2% error. It's not a big deal. Whereas if you're thinking of making a 20 micron passage and you have made 2 micron error in there, it has either increased the size or decreased the size by 2 microns, then it's a 10% change in your dimensions, and that can have a strong influence on the performance of the device. So this issue is also not there with our device. And of course, it also reduces the cost of manufacturing because a lot more manufacturing techniques are now available for making these devices. Of course, then we have done detailed characterization of plasma, which is coming out. And we actually find this is very high quality plasma, in fact, better than what we would get from a centrifuge. And these devices are very extensively tested with no issue, nothing of failure and so on. So hopefully this example gives you an idea of how to go about in detail. So we have talked about a lot of details about how one can go about making a device. And so now what I will do is talk about other devices that we have made in the past. Maybe not in so much of elaborate discussion will be there, but it will be slightly more summarized. But the first example has hopefully given you a lot more idea about how one can go about doing things. So as a further objective, what we would like to have is not just plasma, we would like to have a device which can either give us a platelet-rich plasma or a platelet-poor plasma. So platelets, as we know, are very important uh, components of blood. They are not that abundant as RBCs, but they are still reasonably abundant. But they are very small in size, much smaller than the RBCs, almost 4 times smaller, 1/4 of their size. So, and of course, these platelets are used for clotting of blood. So it becomes very important during surgery and several other procedures. And we also know platelets are very important when we talk about diseases like dengue, which is, of course, unfortunately quite widespread in our country. So in dengue, for example, platelets have to be given from the patient. The other components are not really required. So selectively, can we take and give platelets from one donor to the patient, and without, and maybe the remaining blood can be given back to the donor, and only the platelets are be extracted from the donor's blood. So that is a type of statement, that's the type of problem that we are now looking at. So you can see that this is the device that we had come up with. Again, I'm now no longer getting into a lot of details here, because we have already sort of talked about the principles on which comes in when the blood flows in these small passages. And so we will essentially look at the flow cytometry results, where again we have these 2 lobes. Earlier our focus was on this lobe. Now our focus will be on the other lobe, which corresponds to platelets. So these platelets, you can see that when we go from, this is whole blood, and this is what is coming out from this device on the left, shown on the left. And when you look at these devices, or this window here, you can see that this window has now enriched platelets, which is what we would like to have. And of course, this is how things would look like, blood, and this is how what you would collect at the end. And if you were to quantify how much of enrichment of platelets have happened, so we look at how much has been put in. So if what is being put in is 1, how much are we getting after passing the blood through this device? And we see that we get like 11 times. These are various designs or various designed on slightly different philosophies, which we are not getting into. But it sort of shows that we can get almost 15 times enrichment here with this device here. Whereas our clinical requirement is something like 3 to 8-fold enrichment should happen. So you can see that this device, or in fact, all these 3 devices are already doing better than that, or at least able to provide you clinically enriched platelets. And of course, we sort of have seen how this device works. Now, as a further quantification of the quality of the platelets, this is a very interesting or a very important check that we'll have to do, whether what we are actually getting out from the device is of good quality or not, and therefore can it be administered to a patient or not. So we do this test where we look at whether the platelets are getting activated, or they should not be getting activated. That's what we want. So we would like to see whether the platelets are getting activated or not. So here there are 3 curves which are shown. One is the input sample. The other one is my centrifuge sample. And the third one is the one which is coming out from my device. So my inlet is my green. So this is how, so we would like to maintain everything close to this green itself. So this is, what is there on my axis is not very important. So essentially, we are looking at the green curve, and we don't want this green curve, the deviation from this green curve. Now, what we see is if we were to take the same blood, one part of this blood, and pass it to the, then we would find this red curve coming out. And this is substantial deviation from the green. This is even a centrifuge. This is a known problem with centrifuge. Centrifuge activates about 50% of the platelets. So that means that only half of the platelets that you are actually collecting are useful. The remaining half is not useful for you because they have already activated. They are already activated platelets. Now, what happens in our case with our device, you see that this is a blue curve that you get, and this blue curve shows less than 6% activation. So you can see that, of course, there is some amount of activation, but this is less than like 6%, which is very, very much tolerable. So in some sense, it is even better than a centrifuge. So, I mean, to summarize the first part, we can have this blood plasma separation device is what we have talked about. We've also talked about platelet-rich plasma micro device, which can deliver 15 times enriched platelets. And it's a very simple design to use and operate. And we have not talked about the other device, but we can also obtain platelet poor plasma micro, or we can make a platelet poor plasma micro device as well. So let me just see how much time I have, and according to that, we can decide how far to go.
10 more minutes, sir.
Okay, fine. So I will talk about this device further. So what we will talk about next is a hydrodynamic focusing device. This is also a very interesting idea, and because maybe most of you are from electronics, and so this may be just useful to understand why we would need a device like this, and how would we go about making a device like this. So the problem statement is the following, that let us say there is blood which is flowing, and this is coming from a patient who potentially has a disease. So the way we are going to pick up that disease, and of course we would like to know whether the person is actually having the disease or not. So the way we would like to go about solving this problem is to take the blood sample from the patient and look for anything, and look at the cells which are there, and see if there is a foreign cell or foreign thing which is present in the cell. Okay, it could be a cancerous cell, it could be any other type of cell which would normally come to the bloodstream. So that's a problem statement. So it boils down to looking at various cells and looking at measuring their properties, maybe whether the property is size, whether the property is shape, or whatever else it is, and trying to compare it with the database and saying that all these are healthy cells, whether it is WBC, white blood cells, or the red blood cells, or platelets. Or there are several other type of cells which are there in blood. If I can find those cells in my database, then the patient is okay. Otherwise, okay, somehow my screen has gone. No, okay. Otherwise, if I don't find that cell in my database, then maybe I will have to probe further and say that this person is probably carrying a disease which needs, and the patient needs further testing. So you can see that the problem statement is what it boils down to is trying to measure the property of various cells. But before I do that, and because we've already seen that there are so many of these cells in there, so millions of these RBCs themselves are there, so I have to somehow separate them out. I have to I should be able to just probe one cell at one time, so that I know unambiguously that that's a property that I'm measuring. So that's what it boils down to, being able to separate out these cells from one another, which means that I should make them flow in a single file. Okay, so it's like instead of having a crowd coming and passing through you, where it's very difficult to spot whether the person I'm looking for. Instead of doing that, if I make the people move in a single file, so that then I can look at each person individually, and then I can determine whether that person is who I'm looking for or not. So the issue boils down to looking at making things flow in a single file. Okay, and that's why what you see here is what you get is a hydrodynamic focusing. So what I'm now going to do is, instead of having to work with this sort of a width, which is where So many of these cells are there, so much of crowding of cells is there. I would now like to have a file, single file in which things are flowing. Okay, and of course, you can see that going from here to here is a focusing, just like in optics we have focusing, we can call it as a focusing. And this is an hydrodynamic focusing which is happening. And this focusing is being facilitated by two side streams, which are maybe flowing at which have much higher momentum, and therefore they are able to compress this main stream into a thinner part. Okay, so we will call this as a hydrodynamic focusing. Now, this looks like very straightforward. What is the major thing here? This is something anybody can think about it. So the difficulty lies in the next step, which I'm going to describe, is, so once we have understood that this is what I want to focus it. Now, I'm going to look at the cross-section of the device that I was showing in the previous slide. You can see that this is where the side stream or the sheath fluid is coming. This is where the blood is coming in between. And you can see from the top to bottom, there is a single, or the blood is essentially getting crowded, not in this entire cross section, but now along this line here. So what I would like to do further is to compress it from the top as well. Okay, so that I get a spot like what has been shown here. And then once I put my probe, of course, I would ideally like it to be of one cell size, 8 microns, sort of this ideally should be 8 micron in size. But I would like to reduce it to as much as possible. And so therefore I can measure the individual properties. So what we have here on the left is two-dimensional hydrodynamic focusing. We are only compressing it from one side, whereas here we are compressing it from all sides. And we call it dimensional hydrodynamic focusing. Sorry, somebody is trying to say something here. So this three-dimensional, although you can see that two-dimensional hydrodynamic focusing is straightforward, three-dimensional hydrodynamic focusing is not that straightforward. And again, there are some designs in the previous slide, which we did not go through because of paucity of time. But what you would realize is that these are all complex designs with the several limitations. And major being that either they need several number of these pumps and accessories to have multiple inlets and outlets and so on, or they are complicated to fabricate and so on. So we would like to overcome these, and our target would be to employ only 2 pumps. We have seen that there will be a sample fluid, there will be sheath fluid. So we need a minimum of 2 pumps, and it should be a simple design, and we should be able to demonstrate it with various types of situations. So I know I'm running out of time. So what I will quickly explain our device and how it works, and then we will wrap up. So what we'll see here is that there are 2 things, 2 inlets, one where the sheath is coming. Sheath is a surrounding fluid. This is our blood or the main sample or the sample of interest. Both of them are brought in from this teeth thing. And then because of the much higher flow rate of the sheath, it occupies a larger cross section like what is shown here in 1. So most of the cross section, you will see this black, and very small is this red fluid which is sitting on this left side, because that's how this red would be. After it bends, it will be sitting on this side. Now you pass it through this curve, and this curve introduces a certain amount of vortices. Maybe we don't have time to get into that, which converts this vertical line into a horizontal line. And then you pass through another curve, which brings in the centrifugal effect. And then you get this elongated shape into a tight spot, okay, like what we wanted to do. So this is how the vertical thing gets converted to a horizontal thing. If there is question, we will discuss that. For now, we'll move ahead and show that one can do this with particles, do simulations. We can do detailed experiments after fabricating a device like what is shown here, and then do these detailed experiments like what is shown here using confocal microscopy, where one measures in different planes and then stitches all these planes together to get an idea of how the cross-sectional flow in the cross-section is. So you can see that this is the type of thing that you would see when it is passed through your device. And if you
Sir, screen is not visible, sir.
Screen is not visible?
Yes, sir.
Oh.
No, only for last few minutes it wasn't visible, sir.
Okay.
But I thought you're going to conclude, so you didn't deliberately post it.
Okay. No,
Not a problem.
Okay, I'm sharing my screen anyways. So, okay, so I think we will not get into more of that. So I will just sort of stop here. So, I mean, I basically, we wanted to, okay, let me see if I can reshare my screen. Otherwise, we'll. Is it showing up now?
I think it needs some more time to upload.
Okay, so I think you have gotten an idea of how one can make these biomicro devices. And then, as we said, that these biomicro devices are important because of the various functionalities one can impart to them, and hopefully do a lot of this testing which is being done in the lab at home. Okay, and with much fewer amount of sample of blood and other things and reagents. So I think that's the basic bottom line, takeaway message my talk here. And I will stop here and I will be happy to take any questions.
Can the same device be used for separating the cancer cells, sir? For slight modifications?
Yeah, so that's actually a very good question, and that is something that we are working on. So it has its own limitations. What happens is that these cancer cells are very few in number. I mean, we have already seen these are like millions of these cells in RBCs. Compared to that, their number would be a few tens or even a few ones, like 7, 8, 10 in number. So actually, sifting sifting those very few cells, cancer cells, compared to all these total cells is where the challenge lies. Yeah, we are working on that, and there are several designs which have been proposed in the literature which one can look at. But that's a very interesting problem statement to look at.
Any questions from participants? Either you can put it in chat box. Sir will be there for another 1 or 2 minutes. You can find Sir's details in Wikipedia as well in his website, IIT Bombay, Mumbai. If you need anything, yeah, I think it's the web. Even email ID is given in this website. If you are very interested in this topic, I think you can approach him directly. Tina, are you there?
Yeah. So yeah, please go ahead with the question. I don't know if there are any questions here. If not, you can, of course, also mail me later on if there are questions, and I will be happy to answer it.
Thank you, sir, for your words of wisdom and your knowledge with us. Thank you once again. May I now invite Dr. G. Jocelyn Ratnakumar, sir, Associate Professor, EIE Department, SRMIST, to deliver the vote of thanks. Please, sir.
Thank you, Tina. Good morning to all. It gives me an immense pleasure to propose the vote of thanks on this memorable occasion. First and foremost, I thank our respected Pro VC and Dean, who have been a constant support and guidance for all our activities. Thank you, sir. I sincerely thank our chief guest and the guest of honor for this FDP, Professor Amit Agrawal, for kindly accepting our invitation and gracing the inaugural function by his wonderful presentation. Thank you, sir. I express my heartfelt thanks to our respected Madam, Dr. Mala Juliet, HOD and ATAL FDP coordinator, who always stand by us, guide us, lead us, and motivate us in all aspects. Thank you, ma'am. I extend my thanks to ATAL, the sponsor of this FDP. Without their generous financial support, it would not have been possible to organize this FDP. I extend my sincere thanks to all my colleagues, teaching and non-teaching staff, for their cooperation in organizing this event. Last but not least, I thank all the participants for showing their interest in this program. Hope you'll have interesting sessions in the next 5 days. Thank you all.
So thank you.
Thank you very much, sir. Thank you for your time, sir.
Thank you.
Thank
Thank
you.
you so much.